So far, all the problem we are looking at in any cases that we have was that either the pure moment, we have it on the object, or we have the axial load that actually we assume it passed through the centroid of the cross section. When we're dealing with the axial load that says, okay, it's going to be extended or it's going to be, for example, shrink, what we assume, we didn't use it, but what we assume was that that load, that axial load, actually goes through the centroid of that cross section. Now, what we want to start to see what if the it's not going there, or it's going in the centroid, but the shape of the object is in a way that is not always through the centroid. So, for example, one example I have here is that if you have an object that looks like this, like that, and then I'm going to have the load passing, so I have the force F, applied there. So if I look at that force, if I take a look at that, what I have here is that just the axial force is in equilibrium, and if I cut it somewhere here at two ends, so everything is central, everything is like what we had before in graph. But what if I cut it somewhere in the middle? For example, I go ahead and cut it somewhere there. If I go ahead and say, hey, I want to see what's happening here, and cut it at that cross section. So if I go ahead and redraw that part, so I'm going to cut it there. And then I have the and then I have the internal forces, which would be the shear, would be the P, and would be the M. If I want to go and find those internal forces, this distance is D. So I'm going to write the shear equation that I have, the sigma of x is 0. So it tells me that the P would be equal to F. So that's the axial load. Then I have the sigma Fy is 0, which is going to tell me the V would be 0. And then I have the sigma M would be 0. And assume I'm going to call that point C. So it's the point C. So sigma M about C would be 0. So if I write a sigma m about C0, the V is 0, the P doesn't have any moment, and the M would be F times D, correct? So the M would be F times D. So still I have the shear, still the shear is 0. So the shear is 0, still is a pure bending because we don't have a shear there. But now I have a moment. So now I have the axial load. I have moment and axial. So if I want to draw, I'm going to draw that cross section big to see what happened there. For the tension, for the stress. So there are two parts of that. One part is the axial load, and the second part would be so sigma from axial load. So if this is my cross section, let's make it larger. The sigma from axial load is going to be completely tension, correct? So it's going to pull it here. So it's going to be something like that. So it's going to be sigma from the axial load. Then if I go ahead and draw the sigma from bending, so I go ahead and have this M cross section. And then I'm going to have bending, and the bending in this case, if you look at it, the way it's going to be bended is going to be at the top is going to be compression, here it would be compression, and here would be tension. So at the top would be compressive, at the bottom would be tension. So if I go ahead and say here at the top compression, bottom tension, and it's going to go through the centroid, so it's the centroid here. So we have tension here, tension and compression. So it's going to be compressed there, go to the centroid, go down. So it's going to be if I consider my axis here, so it's going to be my x is going to be sigma x, it's going to be y, then here it's going to be sigma x, it's going to be y. So if here, because at the bottom is tension, so it's going to be positive, at the top is compression, so it's going to be negative, so they're going to look like that. And then when I want to see what would be the result, is that I have to go ahead and say, hey, this plus this would be the result of whatever is going to be whatever is going to happen in that cross section. So I have the sigma from axial loading, I have the sigma from bending, then I have to go ahead and put them together. So if I go ahead and put them together, in this case, so I'm going to have something look like this, and then it's going to probably look like something like that. It's going to look something like that. So basically we will add this. So at the bottom part, that both of them are in tension, so we add them together. At the top part of it is in tension, part of it is compression, so we are subtracting from each other. So in this case, if you look at it, there's no neutral axis there. There's nowhere that I can say the sigma is 0 or the tension is, the strain is 0. But this is the way that we draw it. If this one was really big, for example, if I go ahead and so this one was smaller, if I have another case that look like this, and this time, if I go ahead and say, hey, example, this is going to be a smaller. And this is going to be larger. And then if I go ahead and add them together to see what would be the end result. So this time, because this is bigger, so the tension here is more larger than the compression, so I'm going to get something negative here. And then here at the bottom they would be added together. For example, comes there. And then it goes something like that. We have that. So X and Y. And then now if you look at there, I'm gonna have the neutral axis. So that's gonna be the neutral axis. So now I do have a neutral axis, I can see it, it's gonna be there. So, 2 points. First of all is that the sigma x, if I want to calculate it here, the sigma x is plus minus, depend on the direction of what we have. It's a plus minus that p divided by a plus minus my divided by I. So this is how we will calculate the sigma x. So basically we calculate it separately for each case and then we add them together. The second point is that the neutral axis, if we have one, so look at here at the top one, the neutral axis is going to be somewhere up there. It's not going to it's not going to be on the cross section. It's going to be somewhere there if I keep continuing until it gets 0. If it is on the cross section, it's not going to be on the centroid anymore. So the neutral axis will not pass through the centroid anymore. In this situation, the neutral axis does not side with centroid axis. Or simple word, the neutral axis doesn't pass through the center. So 2 points again. The tension, if you want to calculate tension, you have to find the tension from the axial force, you have to find the tension from the bending, and then you have to choose the sign, or you draw it so you know the sign. So any place that they have the same sign, you add them together. Any place that they have the separate sign, you subtract them. So that's gonna be your end result. And then the neutral axis again doesn't pass through the center. Any question? So basically it's combining the tension from axial load we had it in earlier chapter, in chapter 1 or 2 with the bending. So let's look at some example. We have shape like this. 160 pounds. Applying at these points, so it's going to be 160, 160 pounds. And then so 0.5 is the diameter is 0.5. So it says if the diameter is 0.5 inch and the distance between the load and the center here, this is 0.65. So it wants to know what would be what the sigma and so I want to know how much would be the sigma here if I this is point A, that cross section here is point A. Want to know the sigma max at A, sigma mean at A, and I think things look that good. Distance between the centroid and neutral axis, and the distance between centroid and neutral axis. Also want to know that. So if this is the case that want to know what happened there, so I have to go ahead. I have to go ahead and find everything happened. So find the internal forces at that cross section. That's the first step that I want to know. So I have to go ahead and cut it in half. Cut it in half and use the bottom part for some reason, but can use the top part as well. But if I go ahead and cut it in half at that area, so that's what's gonna get. 160 applying on each end. So we have 160 here. 160 there. And then we have the general forces. So here, look at that. There's no shear there, because there's nothing is gonna cut that cross section. There's gonna be only the normal force and the moment. So if I go ahead and say that the normal force that I'm gonna have is gonna be P, it's gonna be P, and the moment M on each of these cross sections. So that's what I'm gonna have at those cross sections. So now I can go ahead and first of all have to find the internal forces. So find internal forces. So the first step that I want to do. So if I write this sigma Fy is 0, what I would get. So P is 160 pounds. Okay, so I have 160 pound tensile axial force. Then if I can go ahead and say M, and this is the, so this is the A. This is the A. So I can go ahead and find, say, the next step, sigma M about A is 0. For either of the case that's here, if I go ahead, the distance between them is 165. So it says that the M, if I get it from here, it's going to be 160 times 0.65. Which is 104, so M would be 104 pound inch. So now I have the internal forces, and then so, okay, I have the tension force, I have the axial force, and I have the bending moment. So again, I have to go ahead and calculate the stress for each of them separately, and then eventually add them together. So first of all, I will go ahead and find so sigma from P. So sigma would be P divided by area, which would be the load is 160. 160 divided by the area, so it's a circular area. It's gonna pi half a diameter square pi, or we can have pi d square divided by. So if I have that, the P sigma Now, if I go and find the sigma for the bending, so the sigma from bending axial load from bending. So sigma is going to be MYIO. Sigma would be MY divided by I. So the sigma would be, the M is 104. The Y is the half of, is from the center to either of the surface. So it's going to be half of the diameter, basically the radius. So it's going to be 0.5 divided by 2. So that's the one. And the I for the circle is 1/4 of pi, again, r squared. 1/4 of r squared, r cubed. 0.5 divided by 2 to the 4. The I for the circle is half of, sorry, 1/4 of, is 1/4 of pi r to the 4. Okay. So it's gonna gives us sigma is equal to 84.75. Yes. Now if I want to see what happened, I have to add them together to see what happened. But the thing is that I have to add them together in kind of, usually it's easier to draw it visually like that, so you see which part is positive, which part is negative, so which part you have to add them together, which part you have to subtract. So if I go ahead and draw that, I'm going to draw the bottom cross section, but this is one the book draw. So if I draw the bottom cross section, so for axial load, I have 815, and it's going to be tension. So if I look at here, it's going to go up. So I'm going to have 815 going up. So that's 850. Then I have to add it with, that we plus the one from the bending. Then I have to look at it to see which part of it is in tension, which one is in compression. So if it's going there like that, it's going to bending like this, correct? So it's going to bend like that. And if it's going to bend like that, the bottom is going to be in tension, the top is going to be compressed. So this part, this end is going to be tension, so it's going to be positive. And the other end is going to be negative. It's going to go to the center. So it's going to be at this end, it's going to be 84.7. It's going to be plus 84.75. And here it's going to be negative 84.75. So now I can go ahead and add them together, so that then it's going to be equal. equal to, and eventually the what's that going to have, and so it becomes, maximal. So the maximum part is where both of the tension is going to be have the same direction. So the maximum is going to be over here, which is this is going to be 815 plus 8475, which would be equal to 9290, and this part is going to be smaller, and this is going to be 1815 minus 8475, which becomes negative 7660. And then I can go ahead and connect these two together. Like that. So the maximum is going to be 9290, the minimum is going to be negative 7660. So now the second part says the distance between the central and neutral axis. So I know that the neutral axis is going to be here, correct? That's the neutral axis. And the centroid is right at the center. We go and assume the book considered y, I don't know why it's considered as y not, but I'm going to just do the same thing so I can read the book. They assume that this distance is y naught. So how can we find the y naught? Where is the y naught? One way is to use the geometry of that shape, the two triangle, and try to find either of these two distances. But we have that distance, we have this distance, you have to try to find that distance either from here or there. So if you find that distance and you know that's going to be the center, you can do it. The other way that we can do it, I'm going to just write it here, and the way the book writes it, is that what's happening on the centroid, well, on the neutral axis? Sigma would be 0, correct? So on the neutral axis, the sigma would be 0. to do that, I know that on the neutral axis, the sigma would be 0. So on the neutral axis, I know that the sigma would be 0. So I'm going to use that equation. So I'm going to say that 0 is equal to that P divided by area plus minus my divided by I. And if you solve it, it will give you the line to solve that equation. Again, if you know that exactly where it's going to be positive, where it's going to be negative, you don't need to do the visual way of doing that. But my experience is that it's less likely that you make a mistake when you draw it visually and you draw it, than you do it that way. Let's look at another example. So, next examples. I'm going to redraw it a little bit different attribute. So assume we have a beam or a member. redraw it a little bit different from what's in the book. So there's a like this. And then there's a load. And there's going to be the force applying here. Bottom of that. That's a P. And this is passing through the point D. So there's a point somewhere there, let's call it D. Assume this is point D. And this distance here is 10 millimeter. And the cross section. The cross section is the one that we had in one of the previous examples. It's going to look like the T shape. The cross section like this. Yeah. Centroid is going to be somewhere here. That's the centroid. And the point D is somewhere here. previous example that we had, this was 38. This was 22. And the distance between these two is not going to be it's 10 and it's 20. So this is 10 and this is going to be 28. I think that's all. So for that cross section, what we know is that the y bar, is the distance is 38 millimeter. The I would be for that, because we have it in another example. It's 868 times 10 to negative 9 meter to the 4. And then we have the cross section of that would be 3 times 10 to negative 3 meter squared. What else do we also have? So these are what we know about that cross section. Also, we know that the sigma local intention, sigma local for tension is, what is this tension? So it's a 30 megapascal. Sigma local for compression is 120 megapascal. Then we want to know the maximum value for the P. So the very first thing that we need to go ahead and find is that we have to find the internal force at the D. So if I go ahead at the D and say internal force at the D, what I have, I'm going to draw the cross section initially to see what it looks like. But what I have is something like that. So the cross section. And cutting it there. So I know the internal forces is gonna be P here, passing through that point, which is gonna be through the point D. Now, if I want to use that equation, the sigma is P equal over A for the axial forces. If I want to say, okay, the sigma for example is the P divided by area, I have to have it on the centroid. That's where I can calculate that sigma is equal P divided by area. If it's not on the centroid, I cannot use that. So if I want to bring it and put it on the centroid, so basically the P is applied here at the D, and I have to bring it and put it on the centroid. So I have to go ahead and say, okay, I want this be equal to same cross section, but the centroid is up there. So the centroid is somewhere here. So that's the centroid. And I want the P to be there. And that's the point D here. So there's a point D. And I want to move the forces from the point D to the centroid. If I move it to the centroid and I want to have the same, if these two, I want these two to be equal, what should I do? Because right now they are not equal. Correct? So how I'm gonna make these two equal? Remember from the statics, if I move the forces from one point to another point, I have to add or subtract the moment that force causes by moving. So here when I have it, there is no moment at that cross section. But if I move it to the P, there's gonna be more moment about D. So here, if I write a sigma M about D, the moment is 0. If I write a sigma M about D, the moment is not 0 anymore. So I have to balance the moment I added to cross section by moving that. So I have to go ahead and put the moment in the cross section in a way that's gonna balance that. So how I'm gonna put that? Look at here. If it is here, there's no moment. If I move it up there, it's gonna cause the moment counterclockwise. Correct? So I have to put the moment clockwise to balance that counterclockwise moment I created by moving the P. So I have to go ahead and say, okay, then I have to add the M as that here. And how much is that M? The M is P times 28 or point 0.028, okay? So that's the moment I'm creating by moving that P. So I'm gonna balance that moment by adding a moment in the opposite direction to counter that. So now I have the M and P, both of them as a function of P on my cross section, correct? Now I can go ahead and start to calculate the effect of each of them separately. So in the previous example, what we did is that we calculate each of them for the normal, for the moment, and then we add them together. So we're gonna have to do the same things here. So if this is my, I'm gonna just draw them first. So if this is my cross section, the sigma from P, it's gonna look like something like that. So I know that in that case, P is actually pushing it, so it's gonna be that way. Then I have the sigma from M. From M. If you look at here, the moment I have on the cross section is going to like that. So it's going to be tension on the top and compression at the bottom. So it's going to be look like something like this. Top and the values. So let me try. So if the centroid is there, it's going through the center. The centroid is there, going through the centroid. It's going to look like this. It passes through the centroid. Together, eventually we're going to get the final results, which whatever. So I'm going to first calculate and see what. So for the sigma from the tension, so sigma is P divided by area. Is the area is 3 times 10 to negative 3, which would be gives us 333 P, and it's going to be compression. So that's a signal for that. Then for here, I will need to calculate the sigma here and sigma here. Let's name them so we know. Assume this is sigma 0, sigma 1, sigma 2. So we know that which one is which. So I assume that's going to be the sigma 0 here. Now if I want to go to the sigma 1 and sigma 2, so the sigma 1 is MC1 divided by I, which would be sigma 1 would be the M that we calculated it. 1028P, so that's the M, times the C1 at the top, which is going to be 22 millimeter from the central to the top. So it's going to be times 0.022 divided by M, which is 868 times 10 to the negative 9, which gives us 710P. And on the top is tensional compression. If this is the M, so on the top is going to be tension. Sigma 2, we got M C2 divided by I, so sigma 2 would be, again, 0.028P, that's the moment, and the C for the bottom, which is going to be 38 millimeter divided by I, which would be 1226P compression. So if I go ahead and draw them there, so what I have is that this is going to be 333P. This one would be 710P, and this one would be 1226P. So now, so these two will be subtracted, so it's going to be a little bit here, and then these two will be added together, so it's going to be much larger, somewhere here. It's going to go something like this. Something like that. So at the top, what do we have at the top? We have here the sigma. If I call this point, assume I call here A, and I call here B. So sigma at the A. Sigma here would be 710 minus 333. There's a P also. 710P minus 33P, which would be 377. And here is going to be the sigma at the B would be, and this is going to be negative, so I'm going to put the negative here, so don't put a sigma. I'm gonna have a negative 20, negative 333p minus 1226p, which would be minus 1559p. So we know that this is tension, because it's positive, and this is compression. Now that I have this value, I can come here and start to compare them with these two. So, on P max, as if we have two different values, one with the tension, one with the compression. So this is for tension. Have that sigma A should be equal, smaller or equal to 30 megapascal. So, in other words, 337p should be equal or less than 30 megapascal. So, therefore, the P max would be 79.6 times Newton. For compression, that the sigma at the B should be smaller than 120 megapascal. So sigma at B is 1559p, should be smaller than 120 megapascal. So the P max would be 7.77777. So therefore we go with the smaller one, which would be this one. So that's going to be the P-max. Question? So usually if you get that visualization right, the rest is not that difficult. Just know which part is positive, which one is part negative, and then have them right there.
cascade, but